Hello and welcome back to yet another video of AKL Academy. This time we will be doing a video on forces, which is part of the second unit of the IBHL curriculum. So let's get right into it. Let's start with free body diagrams. These are going to be extremely useful when given a word problem and you kind of need to keep track of all the forces. So essentially, free body diagrams are used to show forces acting on an object. And so a lot of times you're giving chunky word problems and there's a lot of not necessary, non-essential information, and you just need a way of simplifying it. So I'll quickly demonstrate. So right here, I'm just drawing an object resting on the ground. Actually not resting. I'll make it getting pulled across the ground just to show you more how more forces can be demonstrated. So obviously, since it's on the surface of something, there's going to be a normal force and a gravitational force. Those have to be equal. And then applied force and a force of friction. And then the second one I'm going to quickly draw is just an example of when an object could be rolling down a hill or a slant. All right. Okay, moving on from these examples of free body diagrams, I have a sample problem just showing how to actually use these free body diagrams. So whenever you draw a free body diagram, you always want to divide them into parallel and perpendicular, the parallel and perpendicular components of the force, with whether it's on a slant or just a regular on level ground. So just redrawing it in purple here, you want to draw the components of it, and it's important to know the difference between component and the force itself, because some questions on the exam will ask for the force itself, and when it asks for this, you do not draw the components. So yeah, here it is, everything edited. So here is the vertical component of gravity because it's on an angle, and this is the horizontal component. And this angle, because this triangle right here is a similar triangle right here. It's just rotated a little bit. So it's kind of counterintuitive because this is the horizontal or the parallel part, but it's actually sine because this is theta and then opposite over hypotenuse. So the parallel part is FG sine theta instead of cosine theta. And again, this is just assuming acceleration is equal to 0, which it might not be, but in most cases it is. So for this parallel components, FG sine theta minus FG cosine theta, which is, force of friction cosine theta, because these are the only two forces acting in parallel. And since this is just another similar triangle, but it's translated a little bit further up, there's no confusing thing with sine and cosine going on, and it is just cosine theta, FF cosine theta. So you subtract those two, and if a equals 0, then you can set them equal to 0 and solve for either one, depending on what the question gives you. Similarly, with the perpendicular components, you're going to want to just Fn is perpendicular. So you're going to want to just have that by itself. There's no angle with that. It's just always perpendicular to the surface. And then the perpendicular component of this would be cosine theta, FG cosine theta. Again, subtract, set equals 0. Add both sides by add FG cosine theta to both sides, and then solve depending on what they give you. Okay, moving on from forces to free body diagrams. We have Newton's laws of motion. So there are three laws of motion. The first one being that it's the law of inertia. And then it states that anything in motion will stay in motion. And then also anything at rest will stay at rest until a force acts upon it. And so, I mean, this one's the easiest one to remember and really the most popular. The net force on anything is always 0 until a force acts on it. That's pretty much it. The second law states that the net force is directly proportional to mass and acceleration. F equals ma. So this is this. Let's just highlight that for you guys. This is kind of the second law is just F equals ma. So obviously, the larger the mass, so a smaller mass with the same acceleration is obviously going to have a smaller force than the smaller ball, because it has more mass than it. And then last but not least, the third law states that if a body exerts force on another body or / object, the second, object exerts an equal but opposite force.